welcome to this explainer. Today we're actually going to look right under the hood of modern AI to demystify something called the self-attention mechanism. If you've ever found yourself wondering how artificial intelligence literally comprehends contextual relationships, well, you are in the exact right place. Okay, let's just dive right into our roadmap for today. We're going to hit the context puzzle, move on to the self-attention web, break down queries, keys, and values, look at scoring and scaling, see how we blend meaning together, and then wrap up with the next big challenge. So, starting things off with the context puzzle. To really grasp the solution here, we kind of have to look at a classic grammar puzzle that exposed a pretty fatal flaw in early AI. The animal didn't cross the street because it was too tired. Now, what does the word it refer to? Is it the street or the animal? I mean, for us humans, our brains instantly know that it means the animal. We make that contextual leap without even blinking, one word naturally reaching out to understand another. But historically, machines completely struggled to make this exact connection. And the reason for that struggle basically comes down to how those older systems read. Early natural language processing relied on RNNs, or recurrent neural networks, and these process text strictly one by one, reading left to right, completely sequential. So by the time the system finally got to the word it, the word animal was already buried way back in the past. They suffered from this long-term dependency problem, meaning the broader context was just gone. Transformers actually fix this by throwing the timeline out the window entirely. They replace it with a simultaneous connected web where every single word interacts all at the exact same time. Which brings us right to the self-attention web, and how fixing that old flaw built a completely new foundation for language processing. This whole new paradigm was introduced back in a 2017 landmark paper called Attention is All You Need. And the core philosophy here is just incredibly elegant. Instead of waiting in a sequential line, every single word queries every other word simultaneously, in parallel. Literally nothing gets ignored. Every word gets a chance to pitch in on the meaning of the entire sentence. But before any of that magical attention math can actually happen, words have to become numbers. So each word gets mapped to an embedding. You can kind of think of this dense vector of real numbers as a word's unique personality fingerprint. So if we take a super simple phrase like the cat sat, each of those three words gets mapped into these dense numerical vectors. They then stack up row by row into a 3x4 input matrix that we just call matrix X. And that matrix right there, that's where the whole mathematical journey begins. All right, moving to queries, keys, and values, because the real trick is how we transform that raw input matrix into something the model can actually use to find context. Let's walk through the exact mechanism here, step by step. First, we take our input matrix X. Then, we project that matrix by multiplying it against distinct, learned weight matrices. And this specific operation generates three really vital outputs: the query, key, and value matrices, the holy trinity of self-attention, if you will, that makes this whole thing computationally possible. To humanize that abstract math just a bit, I like to think of these matrices as a conversation. The query matrix is what a word is looking for, basically a word asking the rest of the sentence a question. The key matrix represents what a word has to offer, so it's providing the answer. And then the value matrix just holds the raw semantic meaning of the word itself. Next up is scoring and scaling. Let's step into the math engine and see how the network actually scores these relationships without completely breaking down. So to find the absolute best matches between those questions and answers, we need to calculate how similar they are. We do this by calculating the dot product. Specifically, we multiply the query matrix by the transposed key matrix, and that gives us a grid of raw attention scores. High values mean a really strong relationship between words. Low values mean they're basically unrelated. But there's a huge catch here. When our hidden vector dimensions are large, those raw scores can totally explode in magnitude and just ruin the calculation. And this brings us to a brilliant stabilization trick. Let's say our vector dimension is 64. Those raw scores could easily spike to 20 or 30. If we leave them that high, the network's gradients die, and the AI literally just stops learning. No way we want that. So to fix it, we divide the raw scores by the square root of the dimension. The square root of 64 is 8. Dividing by 8 magically compresses all those extreme scores back down into a healthy, zero-centered range. This single, highly effective step is exactly why it's formally called scaled dot product attention. Right after that, we take those stabilized scores and pass them through what's called a Softmax function.
And Softmax does two absolutely vital things for us. First, it exponentiates the values, which really amplifies the differences between the scores. Second, it normalizes them so that every single row sums to exactly 1. So what we're left with is a perfectly smooth, completely valid probability distribution. It tells the model exactly how much focus or attention to place on each word. Now for blending meaning together. With our attention weights completely dialed in, we can finally step back and look at the finished product.
Just think about how this all distributes for the word the in our little phrase. The final output factor is really just a weighted sum of the values matrix. Every value gets multiplied by the amount of attention it received. So here, that's 61% of the word the, 25% of cat, and 14% of sat. Add all that up, and boom, you have a brand new vector. The word the isn't isolated anymore. It is now deeply enriched and blended right into the context of cat and sat.
And you know what's truly mind-blowing about this? It's seeing how real grammatical relationships just naturally emerge purely from the math we just did. If you map out the relationships for the cat sat, you'd instantly notice really high scores along the diagonal. That's self-attention. Every word naturally focuses mostly on itself to keep its core meaning intact. But consider the off-diagonal scores. There's a wonderfully strong connection between cat and sat. The subject is literally reaching out for its verb. And remember, nobody programmed this thing with grammar rules. It discovered these structural relationships entirely on its own.
Which brings us to the next challenge. We've seen how perfectly this mechanism captures one specific context, but honestly, human language is almost never that simple. So I want to leave you with one final kind of provocative thought here. What happens when a single word carries more than one meaning? Take the word bank, right? In one sentence, it reaches toward deposit, like a financial institution, but in another, it reaches toward river, a completely different concept. Same exact word, totally different world. Since a single attention head can only capture one of these relationships at a time, how on earth do we process multiple meanings simultaneously? How can a word be understood through multiple lenses all at once? Well, that requires a leap to something called multi-head attention, which happens to be the absolute perfect place for you to continue your exploration of modern AI.